welcome to another module in this massive open online course on probability and random variables for wireless communications. So in the previous modules we have been looking at the various properties of random processes. There is a random process which is wide sense stationary, what are the properties of a wide sense stationary random process, and also the power spectral density, the property of the power spectral density of a random process, and transmission of this random process, especially transmission of a wide sense stationary random process through an LTI system, through a linear time invariant system. Now in today's module let us start looking at some special kinds of random processes. So let us start looking at a special class or special kind. So let us start looking at special special classes of random processes, that is random processes which have special properties. The first such special random process is what we call is a Gaussian random process, which is very important to us. The first such special random process is a Gaussian random process. Alright, so we are talking at special classes of random processes, right, and the first special kind of Gaussian random process, which is very important, we are saying is a Gaussian random process. And what is a Gaussian random process? Let us look at the definition. Let us consider a random process xt xt. Now this random process xt is Gaussian, or xt is a Gaussian random process this is a Gaussian random process if you consider xt1, xt2 so on up to xtn, that is if you consider the random process x at t1, t2, tn, that is xt1, xt2, xtn at time instants t1, t2, tn, at time instants t1, t2, tn. Now these xt1, xt2, xtn, these are jointly Gaussian, that is if you consider the random process xt at time instants t1, t2, tn, that is xt1, xt2, xtn. Now these are jointly Gaussian. What does it mean to say that these are jointly Gaussian? That is the multivariate density is Gaussian. So the multivariate density of xt1, xt2, xtn, that is the multivariate density, that is if you look at the multivariate, that is the multivariate density, if you look at the multivariate density, the joint density of xt1, xt2, xtn, that is this probability density function xt1, the joint probability density function xt1, xt2, xtn, which has n random variables, right. This joint probability density function, this multivariate probability density function, this has to be Gaussian, this multivariate probability density function has to be Gaussian for all possible values of n and for all times t1, t2, that is tn, that is this random process x of t is Gaussian for any value of n. We choose t1, t2, tn, that is n time instants t1, t2, tn, right, and we consider xt1 the random process at these time instants, that is xt1, xt2, xtn, and we look at the joint probability density function corresponding to the random process xt at these time instants xt1 at these time instants t1, t2, tn, the joint probability density function, this multivariate probability density function has to be Gaussian, and then the random process xt is known as a Gaussian random process, which holds special importance in communications and especially wireless communication applications. All right. Now, in particular, if we set n equal to 1, this implies in particular for n equal to 1, we must have that f of x t, that is the distribution of x t at time instant, any time instant t, the PDF probability density function of x t at any time instant t must be Gaussian, right. If the joint probability density function at t1, t2, tn for any n is Gaussian, then if we set n equal to 1, it means if we consider xt at any time instant t, the probability density function must be Gaussian. Therefore, this probability density function, this implies that my probability density function f of x of t of x must be Gaussian, that is of the form 1 over square root of 2 pi sigma square e power minus x minus mu whole square divided by sigma square, where mu equals the mean of or expected value of x of t, and sigma square equals variance, the quantity sigma square equals expected value of x t minus mu whole square, that is the variance, that is the, remember this is the variance of, this is the variance of x t. Now, of course, for a general random process x t, both this mean and this variance will be a function of time, correct. So, this f of x t of x, that is this probability density function, we are saying the parameters mean and variance in this probability density function will be a function of time for a general, for even for a general Gaussian random process. Therefore, we have to consider a special kind of a Gaussian random process, which is wide sense stationary. So, for a wide sense stationary Gaussian random process we will have. So, now consider a wide WSS, that is wide sense stationary Gaussian. For a wide sense stationary Gaussian random process, we will have expected value of x t, that is it is stationary in the mean, therefore, expected value of x t equals mu x, correct. Remember, this is wide sense stationary random process is stationary in the mean. Further, expected value of x of t plus tau, the autocorrelation x of t times x of t plus tau depends only on the time shift tau, the autocorrelation depends only on the time shift tau, that is Rxx is a function only of tau, which implies that if I set tau equal to 0, this implies that expected value of x square of t equals expected value of x square of t equals, that is the average power, that equals Rxx of 0, correct. The expected value of x square of t, that is the average value of this, the average value of x square of t, that is the second moment of this, equals Rxx, the average power in x square t, which means what is the variance? The variance sigma square, the variance sigma square will be expected value of, that will be expected value of x t minus mu x, that is the mean square of this random process, which is going to be, as we have shown before, that is going to be expected value of x square t minus mu x square, that is therefore sigma x square equals r x x 0 minus mu x square, that is sigma square equals r x x 0 minus mu x square. Therefore, what we are going to have, the probability density function f of x t of x, which is equal to 1 over square root of 2 pi sigma square e raised to minus x minus mu whole square by 2 sigma square. This probability density function, this is going to be, now if I substitute the values of both sigma square and mu, this is going to be 1 over 2 pi under root r x x of 0 minus mu x r x x 0 minus mu x square under root e raised to minus x minus mu x whole square divided by under root r x x 0 minus mu x square. So, this is going to be the probability density function of f of x t of x at any time instant x, and this is holds for, what is this? Let us recall what is this. This is the probability density function of the wide sense stationary Gaussian random process, that is the random process x t, which is both Gaussian and in addition to being Gaussian it is wide sense stationary. Then this is the probability density function of x t, that is for any time instant t. This is the probability density function of x t at any, that is PDF of x t at any time instant t for a Gaussian, that is for a special class of Gaussian random process which is also wide sense stationary. So, it has to be both your Gaussian random process and it also has to be wide sense stationary, and then we have this kind of a distribution. We have f of x t of x equals 1 over square root 2 pi r x x 0 minus mu x square times e raised to minus x minus mu x whole square divided by r x x 0 minus mu x square. In fact, there will be a factor of 2 because it is 2 times sigma square, there will be a factor of 2. Alright. So, this shows the probability density function of the wide sense stationary Gaussian random process x of t at any time instant t. Okay. Now, let us consider another special kind of special class of random process which are known as a white random process, which is also frequently termed as white noise. Although in general any random process can be white, typically it is the noise random process, that is the noise in communication systems and wireless communication systems etc., which is white. So, this is also typically termed as white noise, simply as white noise, which can be, which actually be, strictly speaking, should be a white random process. Okay. So, what is a white noise? So, the other thing that we want to talk about is white noise, which is also basically any white random process. What is a random process? A random process is white if if random process white, if it is White and stationary, and the autocorrelation function, that is Rxx tau, is such that Rxx tau, remember this is the autocorrelation, for a white random process this autocorrelation is simply equal to eta by 2 times delta tau, where delta tau, remember this is the impulse, at tau is equal to 0. So, we have our autocorrelation Rxx of tau. In addition, for a white random process, when is the random process white, or when we call a random process as white noise, if the random process is first WSS, that is it is White and stationary, and more important and moreover the autocorrelation function Rxx tau is equal to eta by 2 times delta tau, that is it's basically an impulse function, that is an impulse at tau is equal to 0. Therefore, if I plot it, if I plot this autocorrelation function, it is going to look something like this. Autocorrelation function is going to look something like, so this is my tau axis, this is my Rxx of tau, and the autocorrelation function is this impulse which is delta of tau. So, this is basically your impulse at tau equal to 0, and this is 0 everywhere else, and observe that this implies this kind of autocorrelation, observe that this also implies that this, observe that this implies that is Rxx tau is equal to 0 if tau is not equal to 0, that is Rxx tau is an impulse at tau equal to 0, which implies it is 0 everywhere else. Therefore, Rxx tau is equal to 0 if tau is not equal to 0, and what does that mean? That means that basically except, that is Rxx tau is 0, that is 0 except for, that is this is 0 except for tau equal to 0, which implies, which additionally this implies, basically this implies expected value of xt into xt plus tau equal to 0 if tau not equal to 0, right. Expected value of xt into xt plus tau is equal to 0 if tau is not equal to 0, that is for any non-zero shift, that is for any non-zero shift tau, the correlation between xt and xt plus tau is 0, right. So, for any non-zero, so what does this mean? This means that for any non-zero shift tau, for any non-zero shift tau, that is tau not equal to 0, correlation between xt comma xt plus tau is equal to 0. Okay. So, xt, and which also means that xt and xt plus tau are uncorrelated for any tau not equal to 0. So, this also means that xt correlation is correlation is 0 is basically another way of saying that xt and xt plus tau are uncorrelated, for they are uncorrelated for any tau not equal to 0, that is for any, that is expected value of xt times xt plus tau is equal to 0, if tau not equal to 0, which means xt and expected where there is a correlation between xt and xt plus tau is 0 for any non-zero shift tau, which means xt and xt plus tau are uncorrelated when tau is not equal to 0. That is xt1 and xt2 at two different times t1 and t2 are uncorrelated. Now what is the power spectral density of this white noise? Let us look at the power spectral density, the PSD of white noise, which is basically, remember PSD is, what is PSD? PSD is your power spectral density. The power spectral density of white noise, remember the autocorrelation, power spectral density is nothing but the Fourier transform of autocorrelation. Autocorrelation is eta by 2 times delta tau, correct. And now if I look at the Fourier transform of delta tau, we all know the Fourier transform, if I look at the ft Fourier transform of delta tau, what is that? That is equal to 1 over the entire, that is unity over the entire frequency range. Therefore, if I multiply this by eta by 2 delta tau, the Fourier transform is eta by 2 over the entire frequency range, that is minus infinity less than f less than infinity. This is also for minus infinity less than f less than infinity, alright. So, the Fourier transform of eta by 2 delta tau is simply eta by 2 over the entire frequency range. Therefore, the power spectral density of white noise, which corresponds to the autocorrelation of the, which corresponds to the Fourier transform of the autocorrelation, is simply eta by 2. So, if I look at the power spectral density Sxx of f, what is this? This is nothing but your x, this is nothing but your Rxx of t, and this is your Sxx of f, right. So, this is your Rxx of t and eta by 2 is your Sxx of f. So, Sxx of f is eta by 2 minus infinity less than f less than infinity, that is basically what is it saying, this is equal to eta by 2 over the entire this is equal to eta by 2 over the entire frequency range, and therefore, if I draw this schematically, it looks something like this. I have the frequency range, it is very simple, it is simply equal to, what will this be equal to? This will be simply equal to the constant eta by 2, and what is this? This is your Sxx of f for white noise. Remember, this is not Sxx of f for any general random process, but for a white noise random process. And why is this called white noise? Because remember, what is white noise? What is white light? White light is something which has uniform power distribution, that is, which has uniformly spread over the entire frequency range, that is, it has all color components corresponding to all the frequencies. Therefore, if you look at the spectrum of white light, white light has power over the entire frequency range. Therefore, white noise similarly has uniform power distribution over the entire frequency range. So, this is uniform over the entire frequency range. This is uniform over entire frequency range, and hence that is similar to white light, similar to white light, hence this is white noise. Hence, this is white light because this is similar to white light, and therefore, its power spectral density is uniform over the entire frequency range. So, we have looked at two special kinds of random processes, one is a Gaussian random process and the other is a white random process. Now, if a random process or if a noise random process is both Gaussian and white, it is known as a white Gaussian random process. process. So, that is very simple, and now we are looking at a very, very special kind of a random process. We are looking at white. What are we looking at? We are looking at white Gaussian noise, which basically implies a random process which is both Gaussian and white. This is known as a white Gaussian random process, or typically this is also white Gaussian noise. So, a random process which is both Gaussian random process and a white random process. Remember, naturally, since it is a white random process, we expect it to be a white and stationary random process. So, which is both Gaussian and white, such a random process is known as white Gaussian noise. So, we have white Gaussian noise, that is any random process xt which is both, you have to have your Gaussian property, that means the statistics are, the PDF is the joint PDF at time instance t1, t2, tn is Gaussian, and it is also white meaning the power spectral density is equal to eta by 2. Such a random process which is both white and Gaussian is known as white Gaussian noise, and this is especially important in communication systems because we consider additive white Gaussian noise. So, let us demonstrate a simple application or an example of this in the context of communication systems. Let us look at its typical communication system. We consider in AWGN. So, let us look at an example in the context of communication systems. We consider what is known as an AWGN. Channel, where AWGN, this stands for additive white Gaussian. This stands for AWGN, stands for additive white Gaussian noise. That is basically, if I look at my channel, so let us say I have a transmitted signal x of t. So, I have a channel, or I have my receiver which is adding the noise n of t. I have x of t which is my transmitted signal, and which is I have my received signal y of t. So, what is this? X of t is equal to, my x of t is the transmitted signal. What is my y of t? Y of t is equal to my received signal, and n of t, this is your Gaussian noise. So, we are considering a simple application from a communication system, that is x of t is the transmitted signal, y of t is the received signal, and the noise n of t we are assuming it to be Gaussian. Further, look at this schematic, we are saying the noise is adding to the signal x of t, that is the received signal is x of t plus n of t. The noise is adding to the transmitted signal x of t, therefore, this is additionally known as Gaussian noise, additive Gaussian noise. So, we have the system model for this is y of t equals x of t plus n of t. So, this is basically your addition operation, therefore, this is additive this is additive Gaussian noise, alright. That is additive in the sense that NT adds to the signal XT. In addition, if this noise is white, that is this Gaussian noise is white, implies its power spectral density equals eta by 2. If the power spectral density is eta by 2, that is, if you look at the power spectral density SNN of f, that is equal to eta by 2 over the entire frequency range, then this becomes, that is this additive Gaussian noise plus whiteness becomes your additive white Gaussian noise, which is simply represented as, this is one of the most common and one of the most popular models for a communication channel. This is known as an AWGN, and such a channel which adds AWGN, that is such a communication channel which adds additive white Gaussian noise to the signal XT, that is known as an additive white Gaussian noise channel. Such a communication channel, that is such a communication channel which adds AWGN to transmit signal to the transmit signal XT is termed as, what is this termed as? This is termed as your basic AWGN channel, and this is the most popular model, that is your Y equals, that is your Y of t received signal equals transmitted signal, transmitted message signal plus the noise signal. This is a most popular model typically employed. This is a popular model typically employed to model a conventional wire line, that is in which there is a wire line conventional wire line communication. So, what we are saying is this model Y equals XT plus NT, which is an additive white Gaussian noise channel model, is typically employed to model a conventional wire line communication channel. What is a wire line communication channel? A communication system in which there is a wire or a wire for a transmission medium as the transmission medium between the transistor and receiver. What is the reason that this is employed only to model wireline channels? The reason is because this lacks the fading, the additional impact of what is known as the fading coefficient, which arises in a wireless channel. So, this is only used to model a wireline channel, because since observe here there is no, reason being there is no fading coefficient, reason being there is in an AWGN channel there is no, that is in this simple AWGN channel there is no fading coefficient, correct. If additionally we incorporate a fading coefficient H, this becomes a wireless channel, right. This additive white, in addition to the additive white Gaussian noise, if we incorporate the effect of a fading coefficient H, this becomes the model of a wireless channel. Therefore, additive white Gaussian noise, that is the noise process at the receiver, which is additive, that is adds to the signal, which is Gaussian in nature, and also which is white, that is its power spectral density is uniform eta by 2, is a very important and a very special kind of random process which is used extremely commonly, which is one of the most standard noise models used in typical communication systems, that is both digital communication systems as well as wireless communication systems which incorporate fading. Alright. So, this is your typical model. What I am saying is this is your typical model, this is the typical model for a conventional digital communication system, that is yt equals xt plus nt. Okay. So, what we have seen in this module, we have seen several aspects. We have seen special kinds of random processes, that is xt is a Gaussian random process. If the joint statistics are Gaussian, that is if you look at the multivariate density of xt1, xt2, xtn at time instance t1, t2, tn for any n and any t1, t2, tn, that has to be Gaussian, correct. And a white random process, which means its autocorrelation is basically an impulse at tau equal to 0, which means the power spectral density is uniform over the entire frequency range. And if a random process, typically noise, is both Gaussian and white, it is known as white Gaussian noise. And an additive white Gaussian noise channel is a channel which adds this white Gaussian noise to the signal x of t, that is used to model, that is very frequently used to model communication and wireless communication systems, and therefore, it is very important in the context of communications. Alright. So, we will stop this module here. Thank you very much.